All right, how's it going, everybody? I am here on Monday, April 5th. We're going to talk about section 8.3 today as our second topic for week 11. In the previous video, we talked about the law of sines. Today, we're talking about the law of cosines. These two things are very closely related. This is a really nice, like, single unit week right here of two super closely related topics. This is our second component for helping us solve non-right triangles. So in this section, it's going to feel very, very similar to the previous in that we're going to draw a non-right triangle. We're going to drop an extra line within that non-right triangle to create two right triangles within it. We're going to use those two right triangles to help us formulate a new formula that helps us relate the sides and the angles of the non-right triangle. And that's going to give us a formula that's going to help us solve some other cases. The only distinction is that we want to help solve some different cases than we were able to compute with our law of sines formula. We want to come up with a kind of our last set of cases that we were unable to solve using the law of sines. We're going to get those out of the law of cosines today. So in the previous video, we derived the law of sines, which we could state as the sine of A over A equals the sine of B over B. And I typically like to write this with all three settings right here, even though it's not typically written as like the triple equality right there. This is just to say for any general triangle, you can set up any of those two, it's like pick two out of those three parts that you want right there, set up your equality, solve for your desired component right there. So this is always going to have four components, right? You're always kind of picking two out of the three right here. And so there's always four components that are involved. Since there's two side lengths and two angles out of your four components, it's always going to help us solve scenarios where we know three out of those four parts, meaning two sides or two angles and one angle and one side. Um, so what that means to me is that the remaining category of non-right triangles that we cannot yet solve are the situations in which we know all three sides. So again, and just ignoring like the sine of C over C, if you knew all three sides, then that's like knowing A and B. But if we don't know at least one of the angles, then it seems like we can't use the law of sines to help us solve that triangle to decide what should the three angles be. So basically, this is saying the law of sines is really good, really practical, and pretty simple to use. But in the case where we know all three side lengths and none of the angles, this formula doesn't have the correct like combinations of variable components to help us solve that type of triangle. So what our goal is today then is to derive a related formula, something that's similar to the law of sines. It's going to be the law of cosines. And what it's going to have is rather than having, and again, just ignore the sine of C over C right here. Notice that the law of sines has two angles and two sides. The law of cosines needs to have in it three sides so that we can take in side information and solve for an angle. So what I think is going to happen here with the law of cosines that's a little bit different is that the law of sines is two angles, two sides are what's in the formula. The law of cosines is going to be three sides, one angle is what's going to be in the formula. Slightly different information right there, right? So our derivation of this is going to be relatively similar to what we did with the law of sines. We're going to draw a non-right triangle. We're going to drop down an extra vertical line within the triangle to create some right triangles where there weren't any before. That's going to introduce new variables for us to deal with, but it's also going to help us use our trig functions to establish our relationship. So that's good for us. This derivation is going to be a little bit more. I think that the law of sines was like really easy to come up with that formula. This one's a little bit more complicated, but it's really not too crazy right here. I'm just saying it's technically more complicated than the law of sines one was, but it's still not that bad right here. So let's go ahead and derive the formula that we're going to use today. Kind of similar to with the law of sines right here, how we saw, I think when I first did it, I had like A's and C's involved, but I said, oh, just by kind of renaming our sides and our angles, it could have been B's. So it's sort of like there's three different formulations of the law of sines, right? You could have your A's and your B's together, or your A's and your C's together, or your B's and your C's together. In a sense, there's like three different ways that you could state that by picking two out of the three parts of that equality up there. Very, very similarly, there's going to be three alternate formulations of the law of cosines, like three different ways that we could state it, that are really just swapping our variable locations around. But in this one, it's a little bit more helpful for us to think about the three different equations that we come up with for this one. But we'll get there when we get there. So let's go ahead and derive this thing. So as with last class, we're going to start by drawing our general right or general non-right triangle. But I'm going to do something slightly different with this one, which is that I'm going to place it in a coordinate grid here. All right. So what I'm going to do is rather than just drawing this triangle out in space, let's go ahead and place this thing on an axis right here where this lower left corner of the triangle is exactly at the origin right there. So this is going to like kind of stick out right there. Right. So we've got these three locations right here. And what we're going to want to do is do a little bit of coordinate math with these guys to help ourselves out. So I'm going to go ahead and label these guys right here. I'm going to label this angle A. I'm going to label this angle B, and I'm going to label this angle C. That means that we have side lengths of lowercase a, lowercase b, and lowercase c, opposites of those. And again, our issue with all of our law sines, all of our law cosines, all of our non-right triangles is that our trigonometric functions that we've been using all semester, those are defined based on right triangles. And so when we're in a situation where we don't have any right angles, we can't really use them. So what do? We create right angles so that it does make sense for us to use our trig functions. So I'm going to do the same step that we did in the last video, which is I'm going to go ahead and I'm going to drop down an additional vertical line right here. And the reason why that vertical line is helpful is because it's going to help me see some right triangles in here, right? Now there's a right angle right there, and there's a right angle right there. So we've created a right triangle on both the left and the right. These are situations in which it's going to make sense for us to use our trig functions out there. So here's the thing that happened though, is that this overall side length right here in total is B. But what we've done is we've chopped up B into two chunks, and because this is a really generic triangle right here, I don't know how much of the length is on the left and how much of the length is on the right. And so what we're going to do is we're going to sort of chop it and just make some general labels as to what is this chopping location, right? So in this case right here, all I'm going to do is I'm going to say that this amount right here is X, some unknown amount. And this is just the rest of it, right? So if this total length is B, all the way from beginning to end, and we've already used up X of it, then the remaining chunk of it should be B minus X right there. And notice if you add together X and B minus X, you get B for the overall length, which is good right there. So I'm just introducing a new variable name right there, and that's going to be our label of X. And X is going to be the length from angle C to where we drop down this additional vertical line. So notice that X itself is the width of the bottom of this left-right triangle right here. Since I'm calling this X, I think it would make sense for me to call my vertical component here Y. I think we called it H in the last video. I'm going to go ahead and call that vertical component right there Y. So what we're going to want to do is we're going to want to individually now examine the two right triangles that we have created in this setting right here. So the two right triangles that we have now created are one that looks like this. And I want to label all the parts of this one that I know. What I know here is that this is angle C. I don't know my angle up here anymore, right? Because this is angle B, but it got split up into, I don't know how that got split. I do know that this is side length of A right there. I have called this vertical component Y. And finally, you should notice that and again, I just made up a variable to call it something right here. This length from the origin, 0, 0, out to on the x-axis, so it's only x motion right there, out to where we drop down this vertical line, I just called that x. So let's go ahead and plop x into this guy right here, and this is a right triangle right there. The other triangle that we've got right here is our right triangle that is on the right-hand side here. Right here I've got angle A is known, side length C is known. Again, angle B got split up into two chunks. I don't know what that's going to be. Here's an angle Y, or sorry, a side length Y right there. We've got our right angle, and we know that we have, because we decided that this chunk was length X, whatever that is, this remaining horizontal piece was the rest of the length out of the total length of B. So this is what we're going to call B minus X right there. So what I now want to do is I want to do a little bit of right triangle math associated with these two triangles that we've built right here. I'm going to go ahead and just like number these or something like this. I'm going to just call that triangle 1 and triangle 2 so that we can see where my math is going to be coming from for each of the two sets of statements that I'm going to want to find. So what I'm going to ask is, where is top vertex at angle B? I want to find this location. What I know is that C is at 0, 0. I know that A is at, what's A's x value? Well, we call this length right here B. So it seems like the x value at this point A is going to be B, and its height is 0. But where is this point B located? It's unclear. It's kind of floating out there in space. Fortunately for us, we can go ahead and use some trig statements to help us out with this guy right here. So what I'm going to do is I'm going to go ahead and I'm going to reference this first triangle that we built right here, this first right triangle right here. And based on from triangle 1, I'm going to go ahead and make two statements, all right? I'm going to go ahead and say, one, I can identify what is the cosine of angle C, and I can also identify the sine of angle C right here. So the cosine of angle C, cosine of C, cosine is always going to be adjacent over hypotenuse. Adjacent is x, hypotenuse is a. Similarly, I can identify the sine of angle C. And I know the sine of angle C is opposite over hypotenuse. So that's going to be y over a. And remember that our goal was to figure out where is this xy location, right? So all I want to do is solve these equations for x and for y, because starting from C at 0, 0, x units right and y units up. Therefore, xy is the location that's at that point right there. So all I'm going to do is multiply by a on both of these equations, and that's going to give me x and y. X equals a cosine C and y equals a sine of C. So it looks like this is our B location. All right, so we found where that value is actually located at. And that's going to be helpful for us. In a second, we're going to make some length measurements coming up here in a moment. So now for my next question, what I would like to identify is, let's go ahead and take a look at our right triangle here, this triangle number 2, and I'm going to identify a couple more coordinate locations that are on this guy right here. Now that I know what x is equal to, I see that it's this a cosine C, and I know what y is equal to, it's the a sine C, I can throw those values into this right triangle right here. So now I'm going to say, now we can rewrite triangle 2 and sub in the known values of x and y. So I'm going to scroll up a little bit so that we can see this right here. So this is from this triangle up top right here. I'm going to draw it once exactly as it was, and then once with the replaced values sitting inside of it. So here we've got angle A, side length C, vertical height y, horizontal height or length b minus x. Well, now I can write this exactly as it actually is. I know what x and y are actually equal to because we figured it out over here. I have ways of writing x and y only in terms of things I actually care about. And again, I think the thing to encourage you to remember here is this. When we drop down that vertical line inside of this general triangle right here, the good thing that it did for us is it created right triangles, so now we can use trig functions. The bad thing that it did for us is it created two new variables that we have to keep track of, x and y, neither of which are components of actually solving this triangle. So we introduced new variables that sort of make things more complicated, but we created right triangles, which makes things a little bit more simple. So even though we created those x and y's, and we technically need to use them to describe our relationships between side lengths, I would like for there to not be any xy describing this stuff because that's not the terms I care to solve for. I care to solve for our a's, b's, and c's that are out there, right? So now I'm eliminating the x and y from the expression. So this is still side length c, but I now know that y is this a sine of c, right? Similarly down here, I know that this is b minus the x term, which is a cosine c. And because this is because this is a right triangle, the Pythagorean theorem should apply. So it turns out that the law of cosines is really just a more general version of the Pythagorean theorem. Um, So let's go ahead and make our Pythagorean theorem statement right here. We know that it should be the leg squared plus the leg squared equals the hypotenuse squared. And so in our case here, that's going to look like a sine of c squared plus b minus a cosine c squared equals c squared right there. That's my general Pythagorean theorem statement that I can make based on this right triangle that's right here. So let's go ahead and expand this. And this doesn't look like a formula that I ever want to use, so maybe I'm hoping that we can get some things to simplify here. So one thing I'm seeing, when you square a product of two numbers, you individually square them. So a gets squared and sine gets squared. So I'm going to get a squared sine squared of c plus, I'm going to go ahead and square out this binomial here. Remember that when we do things like x minus y squared, we get x squared minus 2xy plus y squared, right? The Batman thing has already yelled at you about that in the previous videos. So I'm just following this format here. I get the first thing squared, so I get a plus b squared. I get minus 2 times the product of each term. So 2 times b times a cosine c. Finally, I get the second term squared as a positive thing, so it's going to be plus a squared cosine of c squared. And that's all equal to c squared. So this doesn't look any better, but there's some nice things that I'm seeing here. One nice thing that I'm seeing, as soon as I see a sine squared, I start getting suspicious that there's going to maybe be some partners that go with that. And what I'm seeing here is a squared sine squared plus a squared cosine squared. Well, it seems to me like we're adding together some sine squared and some cosine squared. So I'm going to do a little bit of rewriting right here. So one thing I'm going to do is let's group together these two squared sine terms right here. So I'm going to be getting a squared sine squared of c plus a squared cosine squared of c. So those, I'm just reorganizing the ordering of those terms. Plus, I've got my b squared here. And I'm just going to write this in a little bit of a better ordering right here. I'm going to write this as 2ab cosine c. Should be equal to c squared. Now, the last little piece of magic that needs to happen here is I'm recognizing that a squared is a component of both of these, so I'm going to factor it out from those two terms. That's going to leave as a sine squared of c plus cosine squared of c, and you know what that is equal to from our Pythagorean identity. And that's just equal to 1. So all I'm getting here, so this is 1. So all I'm getting as my final statement then is a squared plus b, and remember, this is a squared times 1, so it's just a squared. So a squared plus b squared minus 2ab cosine of c equals c squared. And this is what we refer to as the law of cosines. As promised, you should recognize, very first thing, there's two things I want to talk about before we go use this at all. Two things. The first thing that you should recognize is that, as promised, this formula includes 3 side lengths, all 3 of them, A, B, and C, and only one angle, angle C. The second thing that you should notice is that this looks really, really close to the Pythagorean theorem. This looks like a squared plus b squared equals c squared. It's just that there's an adjustment term right here. All right? This is just like your modification term to handle if it's not a right triangle. And in fact, I'm going to say here, notice that in right triangles, we always have C being equal to 90 degrees, right? That's always the right angle in a right triangle. And cosine of 90, what's our horizontal component when we're vertical? It's 0. So for right triangles, this boils down to a squared plus b squared equals c squared. So this is really kind of saying to us, this is just a more general version of the Pythagorean theorem, that works also for non-right triangles. It's got sort of an adjustment term in there to handle if it is not a right triangle, how much adjustment do we want to make to the a squared plus b squared equals c squared formula. You can see that if we are in a right triangle, the total quantity of the adjustment term is 0 because cosine of 90 will be 0. I don't care what you're multiplying by 0, you would get 0 for that entire term. It would just go away. So this is a more general version of the Pythagorean theorem right here. It works in more cases than the Pythagorean theorem works in. It's more complicated because it's got to work in more cases right here. But if you do plug in the simplest possible case of a right triangle, it does boil down to exactly what you know the side length relationship is for right triangles right there. A squared plus b squared equals c squared. So I think a good thing for you to kind of like remember that the law of cosines is a little bit more special than the law of sines in the sense that it's a generalization of a formula that you've previously seen, whereas the law of sines is sort of like a new idea, relatively simple new idea, but a new idea nonetheless. This is a reformulation of an old idea. This is just a beefed up version of the Pythagorean theorem right here to handle non-right triangle cases. So we do have what we wanted. 3 side lengths are present, 1 angle is present. So this says to me if I know A, B, and C, it seems like capital C, angle C, would be the only unknown, and therefore we can solve for it. So the other thing that you should notice is just like we have our multiple different rearrangements of the law of sines, you can choose which pairings you want, A's, B's, C's, you just got to pick 2 out of the 3. Similarly here, we basically, I just like to think to myself, we could have just named all of our side lengths different things right here. And so in general, there are 3 different ways that you could state the law of cosines. And so here's the thing that I feel like this seems confusing to people. I feel like this is a really easy formula to memorize. So here's why I think this is an easy formula to memorize. The things that you need to remember are this. 1, you're going to get all 3 of your side lengths individually squared. We got c squared, we got a squared, we got b squared, and they're all positive. The term that you have that's additional is always going to be a negative. It's always going to be subtracting 2 times the 2 side lengths that are on the same side as the equal sign. So notice b and c are there, b and c are there, a and c are there, a and c are there. The other thing that you should notice is that whatever term is the standalone one on the left, side length c, that's always going to be partnered up with the angle c that's on inside of the cosine. Side length a, side length b, angle b. So this is one of those things that has like a relatively recognizable structure to it, I guess. So when this is by far the most common way to state this is with the c squared and the angle of c over here. But based on the way your triangle's been written, maybe those don't agree with like the labelings that you want them to be. Maybe you want to solve for angle A. Well, if you want to solve for angle A, you just want to use that version. It's just a renaming of our variables that's out there. But remember, if you want to solve for angle A, then that means that side length A is going to be the standalone guy on the other side being squared. If A is over here squared, then that means that B and C are here squared. If B and C are here squared, then that's the 2BC that we're going to get as the coefficient on the cosine term that's right here. So I feel like this is like one of the grossest formulas that I still feel like is easy to memorize because it's always got these kind of like nice matching components right here. And also, I mean, remembering that this is basically just an alternate version of the Pythagorean theorem, you should be able to see the Pythagorean theorem statement within there with just an adjustment term that's going on right there. So however you want to do this, I think that this is a pretty memorable styled formula right here. And so swapping between different versions of it, I don't think is too crazy right there. So let's do some stuff with this thing. Now, one thing I want to point out before we move on is that we sort of set all this stuff up in cases, right? We said, well, case 1 is when we know no sides and all angles. And we said we can't solve those. We need at least one side length piece of information. Then we said case 2 was our scenarios where we knew 2 sides or 2 angles and 1 angle or 1 side right there as our information. And that led us to the law of sines. However, you should notice that if we knew 2 sides and 1 angle, then it seems like that could actually work out for the law of cosines as well. So it does seem like the law of cosines offers a little bit of overlap with the law of sines in that if you knew side angle information, which is what we're going to do first right here, then you could actually use either the law of sines or the law of cosines to help you solve for the next side that you are interested in solving for right there. We can totally do that with either formula. It's only the case of side where you know lowercase a, b, and c or therefore that component of the equation would be known. That's the thing that's new, that's special to law of cosine. So the thing that law of cosines can handle that law of sines cannot is the side, side, side case right here. So example one, I think we should attempt both different ways right here. One with the law of sines, one with the law of cosines, and then example two, we'll try with the only thing that would work right here is law of cosine. So let's go ahead and take a look at this guy right here. Notice, by the way, that this is just me writing the letters in the opposite order of ASS right here. This is our ambiguous case where we got to be a little bit more careful. So let me just say here, with ASS, can use law of sines or law of cosines. Let's do both. So using the law of sines, let's go ahead and set up some statements here for our general triangle. Oh wait, can we use the... Oh no, maybe we don't have our information in a way right here that we can use this with the right, because we don't have a completed pair here, the A's, the B's, or the C's right here, and we can't get other angle information. Maybe with this one, we're just going to go ahead and just use our law of cosines to help ourselves out with this one, because I don't feel like we have the other information that we need right here to get that other component, right? So let's go ahead and draw our general right triangle right here. I think I've been drawn these as A, B, C, and therefore A, B, C. It looks like the values that we've been given here are that this is going to be 60 degrees, that our A is going to be side length 2, and our B is going to be side length 3 right there. So those are the three pieces. That's what's going on here. This is side angle side. That's why that's not working out for us. Let me fix that real quick. Really? Did I seriously have that written wrong in my notes here? Huh, no, I think I just said that, and I'm checking my notes here, and it's not like that in my notes. Okay, so let's go ahead and check out this side angle side guy right here. And again, notice that we can't quite use the law of sines here because we don't have any one of our pairs of information here, right? If I list my solution table right here, A, B, C, then we're given that A is 2, that B is 3, and that C is 60 degrees. Well, in this case right here, you should notice that I can't solve for either of my other two angles because I only know one of my two angles, and I can't solve for my third side because we're not a right triangle right here. So it seems like I want to use a little bit of law of cosines to help myself solve for some other information. So what other information can I solve for? Well, with the law of cosines, I know the law of cosines involves three sides and one angle. The one angle that I know is 60, and so it seems like we can solve for C with the law of cosines. So what I'm thinking to myself here is because angle C is the known angle, that tells me that I definitely want to use our sort of original formulation of the law of cosines here. So I'm using that top version. So we're going to get here our C squared equals A squared plus B squared minus 2AB cosine of C. So let's go ahead and fill this guy out. C is our unknown, so I'm leaving C squared there. A squared, that's 2 squared, plus B squared, that's 3 squared, minus 2 times A is 2, B is 3, and we want the cosine of 60 degrees. And when I'm thinking cosine of 60 degrees, that looks to me to be 1/2 right there. It's just the shorter of the two lengths right there. So I'm thinking we're going to get C squared is 4 plus 9 minus 2 times 3 times 1/2. I'm going to go ahead and just cancel 1/2 with one of those 2's. And so it looks like C squared is going to be 4 plus 9 minus 6. That's 2 times 3. And so it seems like we're going to get C squared equals 13 minus 6, which says to me that C is going to be the square root of 7, right? 13 minus 6 is 7, and I need to take the square root on both sides to solve for C. So I think that I've found my side length C here as root 7. So now what are we doing? Now that we know side length C, it now seems like we just want to find angles A and B. The good news for us is that we have many routes that we could go with this. So I'm going to say, now that we know C equals root 7, we can solve for A and B. And note, I want to back up because I don't want to suggest that we need to do too much work here. So the deal is that now we know one completed partner pair, the C's. So that says to me I could now use the law of sines to solve for another angle. And notice the important thing that I changed right there is that we only need to find either A or B, because once I know one of these two missing angles, then I can get the third by just adding them up to get to 180, right? So we don't have to do, it's not like we have to do two more whole layers of one of these formulas. We only need to use one of these formulas once to get either angle A or angle B. Then we've got enough information to get all of our angles and we're done right there. So let me make at least the statements for each of these guys right here. If I was going to use the law of sines to help me solve this guy, then I'm saying that I want to use my completed partner pair for the C's right there. So I could say, and I'm noticing that the angle is the unknown, so I want angles in the numerator. So I could say something like sine of A over 2 should be equal to the sine of 60 over square root of 7. This is how I could go ahead and solve for A. Once I get A, I can add up my parts and get to B. Let's just go ahead and do this real quickly right here. This is going to give me sine of A equals 2 sine 60 over root 7. And then A should therefore be the sine inverse of 2 sine 60 over root 7. And we can go to our calculator and get this guy here. Let me bump this a little bit more. I'm going to bring up my Desmos calculator up in the corner like I did before. And over here, we're going to get, just get this up here. So I've got for myself a sine inverse of 2 sine 60 over square root of 7. And what I know right now is that my Desmos right now is in radians, so I'm going to go click on the wrench and change this to degrees, and it's telling me 40.89 degrees. If I'm rounding this to just two places, oh, we'll go three places, 40.893. All right, or we could do the law of cosines here instead, right? We definitely don't have to do both. I'm just kind of showing you guys that we do kind of have some options in this case right here. So let's say that I wanted to solve for angle A with the law of cosine. Let me get rid of my calculator here for a minute. So if I want to solve for A with my law of cosines, then what I'm recognizing I can do, coming up to look here, is it looks like this is the formula format that involves A being being the one angle that's being represented, and I want to solve for that angle right here. So I'm going to use this structure over here. So again, what I know is that because I want to solve for angle A, that tells me that side length A is the standalone one on the side. If A is over here being squared alone, then that means this must be b squared plus c squared over here, the other two angles individually squared. Therefore, my remaining component is going to be minus 2 times b times c times the cosine of angle A. And that's kind of what we're all trying to solve for here right now. So let's go ahead and plug in the parts that we know, and we'll solve for that angle of A. I want to scroll up here so I can see the parts that I know. I'm going to read them off of my known table so far. We're kind of pretending like we didn't get that angle A out down here, right? This is just me kind of showing two different routes to get to the solution. So A is 2, so we're getting 2 squared equals 3 squared plus square root of 7 squared minus 2 times 3 times square root of 7 times the cosine of A. So we just got to move a whole bunch of terms over to the left to get the cosine term alone. Then we'll take the inverse cosine to get our answer here. So I'm thinking this is 4 equals 9 plus 7 minus 6 root 7 cosine A. So let's go ahead and subtract over. Let's see, 9 plus 7 is 16. I'm going to subtract 16 over to the other side. 4 minus 16 is negative 12. Is negative 6 root 7 cosine A. And when I divide, but isn't that going to be too big right there? 12 over 6 root 7. Oh no, never mind. I'm being crazy right now. I'm like getting all worried that this isn't going to work out. This is going to work out just fine. I'm going to divide by this negative 6 root 7 on both sides. So I'm going to get 12 over 6 root 7. Notice there's negative on the left, negative on the right. Those cancel with each other right there. And this should be equal to cosine of A. And just to go check this guy out in our calculator here, because I got all scared thinking I was going to get a number that wasn't going to work out. I'm seeing that 12 over 6 root 7 is 0.7559. And remember, it matters that that number was less than 1. I was, for some reason, convincing myself I was going to get like a 1.2, and we know that's too big to be getting out from a cosine function here. So I think I'm going to find here that A is our cosine inverse of 12 over 6 root 7. And if I go do this guy in Desmos, what are we going to get? Cosine inverse. I want the cosine inverse of this quantity here. So cosine inverse of this one. And what do you know? Unsurprisingly, we're getting out that exact same angle that we saw a second ago, 40.893. All right. So we've got that A value in each of our cases here. And again, we certainly don't have to do that both ways. I was just showing both ways so that you can kind of see that this works out either way for that formula to find that last piece of information. So 40.893 is what we got for A. And now all we got to do to find B is just add up to 180. And so therefore, what's B going to be like 79.107? Just doing my subtraction right there. And so I think that'll be our final angle that we needed for this guy right here. Right? Yeah, cool. 79.107. So in this case right here, we used the law cosines to get ourselves started. We then could have either done a second layer of law of cosines or done a version of law of sines. I think that in general, most people feel like the law of sines is a little bit easier to use. But as we saw in the previous class, the law of cosines will introduce some ambiguity sometimes about the solutions that we're getting here. You should notice that if we had considered the other solution here, I guess I kind of want to say this here. So if A being 40 degrees gives us that correct sine value, then 180 minus 40 of 140 should have also been a potential. But 140 plus the previously known 60 is 200, which is too much. So remember that this law of sines does introduce these possible alternate solutions that you got to watch out for. The law of cosines isn't going to do that to you. So if you really don't like that whole like ASS case scenario that kind of screwed with us a bunch last time, you shouldn't because it makes things a little bit more confusing. That type of confusion does not ever crop up with the law of cosines because when we're finding our two symmetric solutions with the law of sines, they are both positive numbers from 0 to 180, meaning they're both candidates to be in a triangle. When we find our two symmetric solutions, oh, I can't do it with my hands. With law of cosines, I can do it sort of to the left. It's always one positive and one negative that are the two symmetric solutions, and we don't have negative angles within our triangles. So law of cosines, when you use that inverse function right there, it will never create the same confusion that was created with the law of sines. So a really important takeaway here is the math is slightly more complicated with the law of cosines, but you never get that ambiguity that we ended up with in the last video with all that law of sines being like, oh, maybe there's zero solutions, maybe there's one, maybe there's two. That won't happen to you with law of cosines because your symmetric other candidate is a negative angle instead of the other component out of 180. Other components out of 180 could be other angles in triangles, so we had to watch out there. So there we go. So that was our first example. We're just going to do one more example here, and we're going to call it a day. So this is kind of our primary case that's associated with the law of cosines. This is kind of what people more strongly associate with the law of cosines, which is a side-side-side case. I just know all three side lengths of my triangle. I don't know any of the angles. Um, so my strategy here, I'm thinking to myself, is since I know side, 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 I have to use law of cosines first to solve for any of the three angles that I want. Once I know one of the known angles, then I now know all my sides and one angle, meaning I have a completed pair, a side length and its opposite angle, and an unknown side, meaning I can then use law of sines to solve for another angle, or we could just do a second iteration of law of cosines to solve for a second angle. Once we know two out of three angles, we just add up to 180 to get the third. So very similar to the last problem, we have to do law of cosines first, then we have a choice of doing law of sines or law of cosines to solve for a second piece of information, and then we get to do the easiest thing possible, add up to 180 to get the third missing piece of information here. So I'm going to be responsible, and I'm going to draw my general triangle. This is my A, my B, my C, my B, my A, and my C. We have been given that A is going to be 4, that B is going to be 3, that C is going to be 6. And so in my solution table, A, B, C, A, B, C, I don't know any of the angles, but I do know all three sides. So I've got A is 4, B is 3, C is 6. So again, we have an only choice is to use law of cosines to solve for A or B or C, right? We need to get one of those angles right there. In general, this is one of those things where it really, really does not matter which of the three that we solve for. We just need to, pick the right formula. I've just for consistency's sake, I pretty much always use this formula if it's going to be applicable right there, because that's just like the sort of the baseline one that I've always memorized, so I don't have to like think about coming up with our alternate formulations right here. It really, really, these are all going to be completely equivalent. So let's go ahead and find angle C just because I think about that one that way. So let's go ahead and do, so I'm going to solve for angle C. That means that I know that the side length C squared is the standalone side length on the other side. Therefore, it's the A squared plus B squared that are grouped together on the right-hand side. Because this is the A and B on the right, I know that I'm going to do minus 2AB before my cosine of C. And remember, the angle inside of the cosine will always be the opposite of the standalone term on the other side. So the C and the C are always going to be partnered up in that way. So let's go ahead and fill this guy out and see what we got. It looks like we've got 6 squared equals, sorry, I'm going to do a thing right now, by the way. And I think our book does this. I can't remember right now. It's definitely the case that since the side, side, side case comes up pretty dang often, for the purpose, and in the side, side, side case, you'll notice we're always going to use law of cosines to solve for an angle. So sometimes people will, instead studying the law of cosines in this way right here, will solve it for the angle C, since it's so common for us to use the law of cosines to solve for an angle. So what I'm going to do is I'm going to do my algebra in general, then I'll plug in my A's, B's, and C's once I've done all the algebra here. So what I'm thinking is I want to subtract the A and B squared terms to the other side. So I'm going to get C squared minus A squared minus B squared equals negative 2ab cosine of c. I'm going to divide everything by negative 2ab. That negative is going to get distributed through this guy right here to give us a squared plus b squared minus c. So notice, dividing both sides by a negative switched all these signs. So c squared was positive, it's now negative. A squared and b squared were negative, and now they're both positive right there. And dividing by the 2ab, and that should be equal to cosine of c. And therefore, it looks like c should be cosine inverse of a squared plus b squared minus c squared over 2ab. Right? So this is a pretty general, this is sort of like the inverted form of the law of cosines right here to solve for an angle. Right? I'll just say alternate version of law of cosines. Right, so we solved for c before we plugged in numbers. Now let's just go ahead and plug in our numbers into this thing right here. So it looks like angle c should be the cosine inverse of, and now I've got a squared is 4, so we're going to get 4 squared plus 3 squared minus 6 squared, all divided by 2 times 4 times 3. And that should be cosine inverse of, so 4 squared is 16 plus 9 minus 36, all divided by 24. So it looks like it's going to be cosine inverse of 25 minus 36 is negative 11 over 24. Let's go ahead and see what we end up getting for this guy right here. I'm going to drag up my Desmos right here, and let's do our cosine inverse of negative 11 over 24. And it's telling me 117.280 degrees. If I round that thing, it looks like the 6 rounds up the 9 to a 0, rounds up that 7 to an 8, so 0.280, 117.280. All right, so we found our angle C. So now that we've found one of our two angles, it seems like we can go ahead and do either the law of sines or the law of cosines to solve for a second angle. And by the way, you should notice that side length C, side length C over here is definitely the biggest side length. It makes sense that it's therefore opposite of a large angle out there. So big angle, opposite big side. Those things should always kind of align in that way like that. So let's go ahead. We can choose, wait, oh, that was the wrong thing right there. Now I'm screwing up my image right here. I want to get me back behind that thing. And let's get Word back on top of Desmos. There we go. All right. So now that we know three sides and one angle, we can use either the law of sines or law of cosines to solve for another angle. Then sum of angles equals 180 to finish. So let's go ahead and do that. I kind of think that it is, in general, easiest to use the law of sines in general. I'm going to go ahead and use an alternate version of this formula instead, just because I think we should. So here's what I'm going to say. We just found that C was cosine inverse of a squared plus b squared minus c squared over 2ab. Right? Isn't that what we had up here? a squared plus b squared minus c squared over 2ab. So what that's going to tell me is that we then should be able to write this, for example, as like b equals, and let's just see if we can shuffle some terms around to figure this out on our own here. It seems like when c was the angle that we were solving for, side length c was the only negative squared term. So therefore, side length b will be the only negative squared term. So I think this will be a squared plus c squared minus b squared. I then notice over here, this is 2 times a times b, where a and b were the two positive side lengths, the two things that weren't associated with this angle over here. So a and c should be the two things right here. So I think 2ac is my appropriate format right there. And so we can get angle b to be cosine inverse of. And now I just want to grab all the terms that I know. I've got a is 4, b is 3, 4 squared plus 6 squared minus 3 squared, all divided by 2 times 4 times 6. I think I got that right? ACB 463, 463 for ACB. Okay, I think we're good there. And so I'm just going to do a little bit of simplification and we'll go to the calculator. B is cosine inverse of, and that's going to be 16 plus 36 minus 9 over 8 times 6 is 48. And I'll do one more little simplification here. 16 plus 36 is 52. 52 minus 9 is going to be 43. And so I'm thinking we're looking at cosine inverse of 43 over 48. So let me drag Desmos back up here. We're going to get cosine inverse of 43 over 48. And that's telling me 26.384 degrees. This is good. I'm glad that we got a really small angle like that because we obviously got a pretty huge angle for angle C out there. So I was expecting to get pretty small angles for A and for B. The fact that I got a 26 makes me feel pretty good about this overall now. So it now looks like, and maybe I'll just restate my solution table over here. We were given that A was 4, B was 3, C was 6. We found capital C already to be a 117.280. We just found B to be 26.384. And so as my final step now we're just going to add up to 180. So I'm going to come over to Desmos here, and I'm just going to do 180 minus 26.384 minus 117.28. And that's telling me 36.336 is the last angle. And so we've got our overall triangle solved for right here. So kind of our big takeaways on this are, there's a few scenarios in which you have to use law of cosines when the information that you have is only compatible with law of cosines. But there's also a few situations that you're going to encounter where you have a choice between the two, and that's fine. There's nothing wrong with that. Pick the one that you want to do to solve. I kind of tried to like write out when I was making that choice here today, so you guys aren't like accidentally convinced that you like have to do one or have to do the other. I have noticed that some of your MyOpen Math problems say things like use the law of sines or use the law of cosines, so blah 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 blah. Maybe they're leading you in the right direction, but maybe you also have a choice. So I'm saying to you, explore this a little bit and see if you maybe some of the MyOpen Math ones you can actually use law of sines when it says use law of cosines. Maybe try it and do it and see if you're getting the same thing. That's the reason why I worked out this one both ways right there, so you can see that regardless of which technique you choose, as long as you've got the numbers to plug into the formula correctly, you should be able to solve either way and get to the same correct answer right there, regardless of which technique you choose. Again, that's not for all cases that this is going to work out that it's compatible with both formulas, but if it is, the choice is yours and go for it with either formula that you prefer to use. Also remember, and like honestly, this is like if you just go into Google and just type in law of cosines, mostly what you're going to see, like 3/4 of what you're going to see is going to be this stuff. But I guarantee you that there are like entire textbooks that define the law of cosines in this format right here because of the fact that the primary thing that we really need law of cosines for is to solve our side-side-side triangles. In those cases, you're always solving for an angle first. In those cases, this is just having already done the algebra for you right there, where we did the algebra in general to solve for an angle right there. So this is also sort of, in a sense, considered a standard form of the law of cosines right here, where we've solved for the angle instead of made it. But then again, I feel like this is good because it's practical because we solve for the angle. But I feel like you're missing something if you ever forget that the law of cosines is basically just an alternate form of the Pythagorean theorem. It's the Pythagorean theorem with an adjustment term to handle the fact that we're not actually in a right triangle anymore. And so I do think that even if you don't use it in this format right here, remembering this format helps remind you like what the law of cosines is doing. Is it's relating all side lengths, and you know a formula that does that. You just know a formula already that does that for right triangles only. Now we have it for all triangles. So to close up today, I do just want to point out that you should have a couple other like questions about like some things that we've seen in this section right here. And so I do just kind of want to state a couple brief things right here. I'm not going to do any more math. You're not going to know anything else. But I think that there's some things that are worth like, I don't know, give me 5 minutes right here. There's some other cool thoughts that I want to throw at you right here. So one thing is, we saw a law of sines and a law of cosines. And so my question is, shouldn't there be like a law of tangents? I mean, was that not like a very, very natural extension to the things that we're talking about here today? And the answer is, yeah, there actually is a law of tangents. But it exists and it can be used to solve for things. So it looks like a minus b over a plus b equals the tangent of 1/2 of a minus b, angles a minus b, divided by the tangent of 1/2 of a plus b. Hopefully you're recognizing right away kind of why we don't really like this formula very much, because even if you knew, and notice that this is kind of like law of sines in that it requires us to know two sides and two angles, two like partner pairs, and if we all we need is one missing piece and we can solve for it. But in this case here, a lot harder to do the solving. If I said to you solve for lowercase a in this, could you? Like it's definitely more difficult algebraically. So there's nothing wrong with this formula right here inherently. It's just that this is much more difficult for us to manage algebraically. It's just way more work to get the same results than if you had just used the law of sines and law of cosines. But this formula does exist. It is derived in a very similar way. And notice like the derivation of our two formulas were like basically the same. We said write a generic non-right triangle, drop a vertical line to create two right triangles, relate some quantities with sine, relate some quantities with cosine. That's what we did to get our answers for our last two sections. A similar thing happens with the tangents, but it's a lot harder to do the math associated with this formula right here. But it's cool to, I mean, I don't know. It's a very, very, very natural question. If we see law of sines and law of cosines, is there a law of tangents? And the answer is yes. It's derived in a similar fashion. It looks vaguely similar. It's got similar components. The algebra just sucks with it a lot more. And since we can handle all of our cases with the law of sines and law of cosines, like I've never even seen a book that references a law of tangents ever, except as like, oh, and by the way, did you know? So that's kind of dumb right there. So we just never really use that. The other question that we should ask is this. Each formula that we have built involved 4 out of 6 pieces of information from a triangle. Law of sines and law of tangents both involve 2 sides and 2 angles. Our law of cosines involved 3 sides and 1 angle. Is there a formula that involves all 3 sides and all 3 angles? And it turns out, yeah. And similar to our question number 1 here, the answer is yes, but we just never really use it because it's algebraically much more difficult, and it's rarely the case that you're going to know 5 out of 6 pieces of information and need to like struggle to find the sixth right here. So we're going to go ahead and again give an emphatic, yeah, there actually is. This is referred to as well, okay. This is one of those things where this guy is certainly, I'm almost 90% sure he's German, so this would be a Malvita's formula right here. Um, Not Malweeds. You Americans out there, that W would be pronounced like a V and like a Vida right there on the end. But in any event, there is this formula that's out there, and it looks kind of crazy, but it technically exists. There's all 3 of our side lengths right there, and this is going to be equal to the cosine of 1/2 of a minus b all divided by the sine of 1/2 of c. So again, this formula is just not nice to solve anything for. We're really rarely in a situation where we know so much information. If we want to solve for a sixth piece of information, one, if the one piece that you're missing is an angle, well, then you should just add up your angles to 180 to get the other one. That's the easiest math we can do. If the thing that you're missing is a side length, it's definitely easier to use the law of sines and the law of cosines to find the missing side length than it is to use this crazy formula right here. So this is just one of those things where, yeah, there is a way to relate all this information. It's just not as practical, like execution wise, for us to care to actually use it. And so we don't, but it exists. There's a dude that figured it out, that relates everything in one nice formula right there. And it's not nice enough to want us to use it, but in my mind, I would envision this formula being a little crazier out there. These are interesting, at least mathematical oddities that exist. Finally, the last question that I want to kind of talk about right here is this question of history. And what I also want to kind of throw out to you guys is, when I was in undergrad, I took a class that was history of math, and then I actually got the awesome opportunity to teach history of math at the previous college that I was at. The history of math is really freaking cool. I don't think that this is me like being some nerd that's cool into nerd history. There are a million like amazing stories that are tied to history of math, and one of the things that's great that I think that makes this appeal to modern day audiences is that if you like seeing two people get in a fight, I promise you there are no better fights in history than massive nerds getting into a fight about who is more right than the other person. And throughout mathematical history, this has happened over and over, where people just hate each other and they're like, that moron thinks that blah 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 blah. And we like have all these archived records from all of these like famous mathematicians. You talk about Newton versus Leibniz and who invented calculus first. Those two guys freaking hated each other and they wrote hate mail to each other all the time. We like still have it all. Such awesome stories in there. So if you like your pulp drama, it's all in the history of math, and like legit like actual fights that people physically got into, duels between mathematicians where people died, having math contests in the street with hundreds of people watching, like crazy things that go on. So I would encourage you, if you ever have the opportunity to take a history of math class, it's super interesting. And so I just want to lay a brief bit of this history on you from some of these things, because I think that another thing that's really cool about the class is that how math has progressed historically is really, for most people, not even remotely close to what actually happened in your mind. What a lot of people think is that the math that seems easy came first and the math that seems hard came later, and it's really, really not even close to that in most cases. There's kind of, I don't know, a lot of like kind of false beliefs that exist about how math progressed historically, and so again, taking a history of math class really like showed me that things didn't quite pan out the way that I thought that they did. So just some kind of statements here about these things. Law of cosines. Law of cosines was first stated by Euclid, which I think is a name that most of us know, even if we don't like really know him. Euclid was a Greek dude, but as a lot of us know, the Greeks and the Egyptians had kind of really close ties, for better and for worse, between 2,500 and 2,000 years ago. So he lived in Alexandria, Egypt, as many, many Greek people did at the time. That's kind of where like a center of a lot of like academia and commerce was happening. And the Greek Empire kind of like, sort of like, I don't want to say owned, but like kind of controlled part of Egypt for a while, or at least had like really strong diplomatic ties with them. So it was a case that a lot of academics that were Greek would go to study at Alexandria. I know that a lot of people are at least vaguely familiar with the Library of Alexandria. That was for hundreds of years sort of like the center of all human knowledge for a long time. And I'll get to a brief story about that here in my third paragraph down here. But in any event, Euclid was a Greek dude who lived in Alexandria, Egypt. He was the very first person to publish any mathematical work that contained the law of cosines. And that was around 300 BCE, right? So 2,800 years ago that this was happening there. And so an interesting thing here to notice is that law of cosines actually came first. Law of sines, in my opinion, is definitely easier, but law of cosines was discovered before the law of sines, or at least had the first like paper like published that contained that as a formula, and that's by Euclid, like a really, really famous mathematician. The next one, law of signs, was then found about 450 years later by another Greek dude also living in Alexandria, Egypt, about 450 years later, named Ptolemy. But which, by the way, not to be confused, there were many kings of Egypt whose name, who like Ptolemy. I think there was something like 10 different Egyptian kings named Ptolemy. I'm assuming he was like named after one of those guys, but he's not an Egyptian king. He's a Greek guy who happens to share a name. And like literally, I think that like Ptolemy was the king like when he was doing this, like Ptolemy the 12th or something like that. But in any event, so he sort of had some computations that technically did the math that happens within the law of signs, but he never like stated the law of signs as like a conclusion that he generally found, largely because he just didn't quite have like the mathematical language, like variables and equal signs and stuff like that to manage it. Then you should be asking, well, then how did Euclid say this stuff 450 years ago? There's lots of different ways that people used geometry to help justify their formulas. Euclid came up with a very good geometric representation of the law of cosines. Um, Ptolemy just struggled a little bit more. So Ptolemy is sort of credited with like the idea of it first, but the first known published work with the law of signs didn't come for another 1100 years out there, by Nasir al-Din al-Tusi, who's a Persian guy, right? So Persia we know as sort of like the old version of Iran. Persia also covered a little bit more than just strictly present day Iran, but that's like a majority overlap right there. So he was born in what's now northeast Iran, some, I don't know, small crappy town that I've never heard of out there. Not like I know lots of towns in Iran, but he ended up going to study in Mosul, which is the current capital of Iraq. It is the capital, right? I'm pretty sure Mosul is the okay. Uh, okay, maybe I'm being overexcited right there. I don't want to embarrass myself with my geopolitical statements right here. But in any event, Mosul, definitely a major, major city in Iraq. And for a long chunk of history, similar to Alexandria in Egypt, was like a hub of academic knowledge, like in the world, like one of the most important places in the world. So my last brief little history statement that I'll make to kind of wrap this up is the library at Alexandria, because it was such a really, really important place, that library in particular. What does that mean when it's important? Well, it means that your enemies want to burn it to the ground. So the Library of Alexandria actually underwent like 5 separate like burnings of the library that destroyed lots of its stuff. Sometimes some of those were accidents, some of those were on purpose, like arson basically by like invading armies trying to burn down the library. There's lots of stories about that kind of stuff. So what ended up happening was, think back in the day before we've got printing press, like a book is like insanely valuable. Like most academic books are literally worth their weight in gold. Like with the knowledge, it takes so long to come up with the knowledge and then to transcribe just even a second copy of it was a huge deal. So like this is like the most valuable stuff on the planet is in the Library of Alexandria around these times. So what ended up happening as it was becoming more and more clear that this was no longer like a defensible position is a lot of these books, either the originals or copies of them, were taken over to places in the Middle East. So there became a time where in Europe, which for a while was like the center of like academic knowledge in the Western world, primarily at least. So a lot of things going on in China and India that didn't intermix so much with what was happening in the West. But in the West, Greece and Rome were like really central places. Italy and Greece were really central places for early math. But eventually, if you guys have taken like a world history class, then you know that most of Europe decided to just like have plagues and go to war with each other as their like primary focuses for like 1,000 years in there, which we refer to as like the Dark Ages or something like that. They weren't dark, that's a stupid name for an era of time out there. But the point is, in that period of time, most of the contents of the Library of Alexandria that were not burned to the ground were all taken to places like Mosul, were taken to places like Constantinople, right? And like places in like Turkey. And so what really happened was all the Greeks kind of figured out all these really good ideas. Then they handed all this stuff off to people in the Middle East. People like in modern day Iraq, Iran is where most of the math then happened for the next like 500-800 years. Basically, what happened there is those people then figured out excellent versions of geometric representations of all these just word ideas that they had in Greece. Then later, once trade routes became established, more around the 1250 to 1500 times, all of this knowledge that was really actually originally European ideas that was improved upon by people in the Middle East, then got brought back to Europe. And so people in Europe were then studying what were originally European ideas from like 1500 years ago, but were reformatted into a better version of it by people in the Middle East. And then those are the Europeans that then invented things like algebra in the 1500s with actually getting variables called like X and Y, equal signs, addition, subtraction signs. Those were all like kind of late in the game inventions by European people after they sort of got all their books back from the Middle East by having a lot more of a rich academic interchange with those people, more in the like 1000s to 1500s out there. So there's this kind of like cool progression of like the Europeans were doing it, but then they really were doing it in Egypt. Once the library in Egypt was getting burned down, it all got carried over to the Middle East so that it wouldn't all get destroyed. They all improved on those ideas. They just ended up with all these books over there in the Middle East, and they were like, "Huh, all this stuff's awesome. Can we do something with this?" And the answer was yes. They improved on it, and then the improved ideas from the Middle East got brought back to Europe, and that's when there was like the sort of the academic renaissance that happened in Europe in like the 15 and 1600s, which ultimately led to 1666 is when Isaac Newton published his book on calculus, and that's sort of like one of the, I'd say one of the 20 most important book publishings in the history of humanity right there is really a lot of his ideas were Greek ideas that brought back to Europe from people in the Middle East right there. So lots of really cool Middle Eastern history that's very closely tied to a lot of European math that happened out there as well. So again, infinite really cool stories that are out there associated with history of math. So if you get an opportunity to take a class focused on that, I would strongly encourage you to do so. It's one of the coolest topics I've ever gotten to take in a class and teach in a class right there. So look more into that stuff. Read the stories in Wikipedia. There's so much cool stuff out there. That's going to wrap it up for me today for a law of cosines here. I do want to point out one brief thing is that in our upcoming videos right here in the next sections, I'm going to diverge a little bit from what our intended plan was for the semester because as I stated in the thing, I was expecting that we were going to get off by a week. We did. That was like last 2 weeks right there. So there were a couple other topics that I am still hoping to cover, but I'm going to push them to the last week of the course if we get there kind of thing. And I'm going to skip on more to some more of the like core content of this class rather than the, I don't want to say that the other stuff is like not important, but it's slightly less important stuff that I'm going to skip over real quickly here. So we're going to be picking up with chapter 9 next week, and we're going to talk about polar coordinates, polar equations, polar graphs will be our 2 videos next week. And again, there's a couple topics that we skipped at the end of chapter 8. We'll come back to those in week 15 if it turns out that we end up having time for those. So that's going to wrap it up for me here today. Have a good one, everybody. I will see you for polar coordinates next week. Have a good one.